last time we introduced the notion of a derivative and we gave the following definition of the derivative. As a reminder, the derivative is the same thing as the instantaneous rate of change, which we talked about earlier, and it's also the same thing as the slope of the tangent line, which was something that we talked about in some of the earlier videos when we introduced average rate of change and instantaneous rate of change. So as we go forward, we're going to use derivative as the terminology here, but you should know that all three of these ideas are equivalent. So in this particular section, because we now have a limit definition of a derivative, we can use some of the algebraic tools for finding limits to find the derivative or the instantaneous rate of change at a point. So we're going to use the example that we did in the last section, where we had the function y equals 3.2x squared, and what we want to find is the derivative at x equals 3, or again, you can think of this as the instantaneous rate of change at x equals 3. And if we plug in this particular function into the limit definition of a derivative, we're going to get the following expression here. And we can use the algebraic tools to find limits, to find this particular derivative. Now, when dealing with derivatives, or I should say when dealing with limits, remember that the first thing you always want to do is try for direct substitution. Okay? Although in this particular example, if you try to do direct substitution, you will get 0 over 0 every single time. This is an indeterminate form, so we will have to do more work. So anytime you deal with problems like this, you really don't have to do this particular substitution because it's always going to occur. So we can go straight to the more algebraic rules, which will allow us to try to factor and cancel. So we're going to do that now. So the first thing that we're going to do, because we ultimately are going to want to try to cancel this h, is we're going to actually try to expand things. So this is going to be the limit as h approaches 0 of 3.2 times, and I'm going to expand to the 3 plus h squared. Just as a quick reminder, anytime you have something that looks like a plus b squared, this is going to be a squared plus 2ab plus b squared. So in this particular example, this is going to be 3 squared, which is 9, plus 2 times 3 times h, which is 6h, plus h squared. So that's a nice, easy shortcut in order to deal with that. And then we're going to compute 3.2 times 3 squared, and if we do that, we're going to get 28.8. And then we're going to divide all of this by h. Again, we're not going to be able to substitute until we cancel this h out, but we can't cancel that h out until we do some more math here. So the next move that we're going to do is we're going to distribute this 3.2 across all three terms here. And when you do that, this is going to result in the limit as h approaches 0 of 28.8 plus 19.2h plus 3.2 h squared, and then we're just going to finish out what we have here. The one thing that you'll notice here is that the 28.8 here is actually going to cancel with the negative 20.8.8 there. And that's actually a very nice thing because now in the numerator we have a whole bunch of terms with h's, and we can actually just factor out the h from these two terms. So when we do that, and it's always important that you keep writing this limit out front, but when we do that, and that's supposed to be a 19.2h there, so make sure you put that in. So that's going to be h times 19.2 plus 3.2h over h. And then the h's here are now going to cancel. And now that we've actually canceled the h's, we can attempt to do this by direct substitution. So I can plug in 0 for h. And when I do that, we're just going to be left with 19.2. So 19.2 is the derivative or the instantaneous rate of change at of y equals 3.2x squared at x equals 3. So this is also what we will call f prime of 3. So just as a reminder from last time, when we found the average rate of change of this function from 3 to 3 plus h, and we chose increasingly smaller and smaller h's, we got the following graph. So at 0.5 we would get 20.8, and as we proceeded down here, we'd actually get closer to 19.2. But notice that these were all approximations, and the 19.2 here is actually an exact answer, which is really nice. This gives us an algebraic exact answer for the instantaneous rate of change at that point. To help us understand this just a little bit better, we're going to do one more example. So we're going to find the derivative of f of x equals the square root of x at x equals 4. And when we do this, we're going to get this particular construction here. And with a little bit of simplification, we'll see that we get the square root of 4 plus h plus 2 over h. Sorry, that should be a minus 2. And now what we're going to do here is, in order to simplify or factor and cancel, we're going to need to get rid of the square roots in the numerator. So to do that, we're going to multiply by the conjugate. That's going to be the square root of 4 plus h plus 2 times the square root of 4 plus h plus 2. So basically what you're going to do is you're going to take whatever your original term is, and you're going to replace the plus with a minus with a plus, or if there's a plus here, you'll use a minus sign. And the reason why we do this is because if you have a difference of squares, something that looks like x plus b times, or a plus b times a minus b, this will get a squared minus b squared, and that will allow you to get rid of the square roots. So just to show that that happens, this is going to be in the numerator. Always write your limit here. It's going to be 4 plus h, because the square root of 4 plus h squared is 4 plus h, minus, and then 2 squared is going to be 4 over, and then we're going to have an h, and then we're just going to leave the square root of 4 plus h plus 2 in the denominator here. As you'll see, similar to what happened in the last example, the 4 and the negative 4 here are going to cancel. And that will also, since there's just a single term left in the numerator, this h will then also cancel with the h down here. So this leaves us with the limit as h approaches 0 of, well, since there's nothing left in the numerator, we're going to put a 1 up there. And this is then going to be the square root of 4 plus h plus 2. And now we can plug in 0 for h. So this is going to be 1 over the square root of 4 plus 0 plus 2, or 1 over the square root of 4, which is just 2. And then this will be 1/4. So this is how you find the derivative of a function by using the limit definition of a derivative. In future sections, you'll see that there's actually a much quicker way to find a derivative that bypasses the limit process. And from that point on, we will kind of step away from limits, but there will be many times in a calc class where you're going to be asked to use the definition of the derivative or the limit definition of a derivative to find derivatives. And because that will be a required type of problem, it's important that you know this process, even though most of the time you will not use this process, but you will use some shortcut rules that will make this process a lot easier. And we will see that pretty shortly here. But as always, I hope that you found this video helpful, and take care.